Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. We are discussing on compressed domain processing, and we will continue our discussion. In the last class, we discussed about block composition and decomposition, and there we have seen how these operations can be done through linear transformation by using a single transformation matrix, so that you can convert M adjacent endpoint DCT. So, here we are considering conversion of M adjacent endpoint DCT blocks to a single M cross endpoint DCT block, and this we can do using a single linear transformation. So, this is one example of this linear transformation, and this I have explained in the last class with respect to 4-point DCT and 8-point DCT. That means converting two adjacent 4-point block to 8-point DCT block, and we are considering in this case column vectors. So, in this representation you may consider this is the representation. You can see that this is the first column vector. Now, since this is a column vector, but for the convenience I am representing it in terms of rows. So, if I convert this transformation, which means x0n will be a block of endpoint DCT in the column form. So, this is that transformation matrix. So, this is x0, this is x0n. Similarly, the next adjacent block will be this x1. So, this is x1n. So, in this way we have M adjacent block, that means this one is M minus 1 adjacent block. So, this is a column vector. Once again, for the convenience of representation in the form of a row, we are representing in this form. So, we are representing, first we are making a transformation, we are taking a transpose or transposition of this column vector into this row form, and again we are performing another transposition to make it a column form like this. So, we are multiplying a matrix of which is given a parameter m and n, but you know that this is the DCT, this is the single DCT block of dimension of length mn. So, this length is mn because this length is also mn, m into n, and in this case it is a DCT coefficients of this mn block. So, you will be multiplying. So, this block would be, as you say, this is mn cross 1, this is a dimension, only one column, and this is a column vector. So, this dimension would be mn cross mn, which means this is a square matrix of dimension mn cross n. So, this composition matrix whose parameter is m and n will be of dimension this. And how this matrix can be computed, can be derived using the series of inversion and inverse transform and forward transform that we discussed with respect to 4-point and 8-point DCT. So, let me provide these expressions in terms of in a generic form of as we have shown here for n-point DCT of m blocks. So, this is that transformation matrix AMN. This is how it is defined, and you can observe that in the diagonal element these are all inverse transformation of n-point DCT, because if I consider a block here, equivalent block, so the first inversion, this row actually inverts this particular column of the DCT columns. Similarly, this row, this position is meant for inverting the second block of endpoint DCT, and in this way it proceeds. So these matrix multiplications will give me actually the spatial domain transformation, inverse transformation. Using this transformation matrix, we can make this kind of block composition of adjacent blocks of M adjacent block of endpoint DCTs. Now, if I want to extend these particular computations in 2 dimension, as you can see that in 2 dimensions, what we can do? So, we can perform the series of column transformations. We can perform each and every column transformation into the row transformation. So, let me explain once again the way we have extended the property for forward transform. Say you have these columns, you are taking actually in this case in a generic form, say this is L adjacent block in the direction of rows, and say this is M adjacent block, say in the direction of column. So, of a 2-dimensional matrix, which means that you have an L cross M adjacent block. So, these are the L cross M of N cross N blocks. In this way it proceeds. Similarly, these are all N cross N blocks. So, when we consider a transformation or composition, so I will be composing this column into a form of this. So, every column first is composed, and then you apply once again transposition to convert them rows. Basically, now if you make transpositions, then these rows will be transformed, which means these rows will become a column. So, these rows will become a column and the columns becomes a rows, which I have drawn here. So, again you apply the same transformation, same merging transformations. So there these things are getting merged, and finally the whole Mn cross Mn block you transpose it to get the original form of the matrix or original information arrangement of the matrix. So this is what you are doing. So if I express them, let me write this block, say this is my input block, which is of size L n cross M n, and there I am transforming it using a matrix A L n. So this will give me this one without transposition, but then I have to make a transposition of this. After transpositions, I will get these columns, and now this length is M n. So this is M n, and the other direction is of course L n, because you have transposed it. So now you multiply with A M n, and then again you perform transposition to get the whole transformations, which means it will become, if I now apply all the transpositions. So first I am converting this one, so which is X transpose A L comma N transpose, and then you are multiplying with M n and performing transpose, which will be, as you know, the transposition order gets reversed. So first I will be transposing this one. So this one will be once again A L N X, and this one will be A M N transpose. So this is how a two-dimensional DCT blocks, set of two-dimensional DCT blocks, they could be merged into a larger block. So let me show you this expression once again. Mathematically. So this is the final result or expression, as I was explaining you how these transpositions or these steps of converting, merging columns and then merging rows, and then you again transpose it back to its original arrangement, will give you equivalently these expressions. So it looks like, as you can see, it looks like a forward transform, and like the way we have used the transformation. The interesting part is that these matrices are, since it is square and these are square and also invertible, so if I apply the inverse transformation, then I will get back from the merged columns to once again the set of decomposed columns. So in one dimension I can perform this inversion, and for two dimension once again your expression looks like this, because if I apply this inversion in this form, you will get back once again the blocks, n cross n blocks of L cross M, n cross n block from a larger block size. From a larger DCT block, you can get smaller DCT blocks with these spatial arrangements. So these two operations are very fundamental operations for DCT processing, because as you know that in our compressed domain there is only particular block size is specified. For example, 8 cross 8, that is what is for JPEG compression, but for video compressions there are macro blocks also is there. So anyway, so in this context mostly you will be working with 8 cross 8 block. So that's why you will be considering 8-point DCT block, and if you would like to see with respect to 8-point DCT block how this composition matrix looks. So if I consider say 2 cross 2 8-point DCT blocks, or just 8-point DCT block for a column vector. So 2 adjacent 8-point DCT blocks to be merged with a single 8-point DCT blocks. So this is what it is giving. Actually it is merging 2 4-point DCT block to 1 8-point DCT block. This I have already explained in the last lecture. So if I look at this particular transformation matrix, you can see that in the transformation matrix there are quite a good number of 0 elements. So which means this matrix is moderately sparse, and this enables us to design certain computations which would be faster than ordinary matrix multiplications, because we can take leverage of this multiplication with zeros. We don't have to multiply anything, simply you can ignore those multiplications with those elements. Similarly, addition also you can if for the addition also it will reduce the number of additions because you have only a few elements there. So in this way the number of multiplications and additions that could be reduced if I perform these operations directly with this matrix for these purposes. Even the inverse matrix also would be sparse, will be also sparse, that you can see. So this is the composition form as I explained earlier. So for with respect to 8 cross 8 block, that means there are 4 4 cross 4 blocks. There are 4 4 cross adjacent blocks, 4 cross 4 blocks, and then you apply this, density composition matrices. This parameter shows that 2 adjacent 4-point density blocks will be merged to one 8-point density block. And this is for 2-dimensional transformation, you have to use this expression as I explained. Similarly, for decomposition, you have to apply respectively the inverse operations, and you can perform these operations. So, with this background or understanding of certain properties of block densities, let us now consider how we can perform the operations like image halving, which means we want to shrink the images half of the size of its width and height. That is image halving. Let us discuss that, and similarly we will also discuss image doubling, which means the image should be enlarged with twice of the size of its height and width. So, first image halving, and two approaches I would discuss following this kind of theoretical framework. One is that approximation followed by composition. So, here diagrammatically I am showing it. Say you consider 4 8 cross 8 blocks. So, these blocks are of size 8 cross 8. 4 adjacent 8 cross 8 block, and my output is a single 8 cross 8 block. So, in this way I am performing image halving. So, the way I am doing, you can see that using subband approximation theory, I can consider only these lower frequency part, that quadrant as I mentioned, and the scale factor will be half. So, if I multiply these coefficients with half and place it like this with this spatial arrangement, similarly this one here, this one here, and this one here. So, this is my I should say resulting operations. So, this image itself, it is a 4-point density of the image, which is of half of the resolutions of this image. This is the size. Now, this 4 cross 4 block I have to do, I can merge it to 8 cross 8 block. So, you see that first what I did approximation. This is a subband approximation, and then after that this operation is composition. So, that is why approximation followed by composition, and mathematically I can write it in this way. So, I can take these blocks by approximations and then perform these compositions. This is how I can perform the image halving operations. So, this is just the description. This is mentioning that this is a subband approximation. Only I am restricting into 4 cross 4 zone of the coefficients, first 4 cross 4 coefficients in the lower segment, and this is the output block by considering each of these blocks, which are indexed as say 0 0, 0 1, 1 0, 1 1. So, this is how this index is referring to these blocks, and this gives you the mathematical description of this operation. The other approach of image halving could be composition followed by approximation. So, first I will compose 4 adjacent 8 cross 8 blocks. So, 4 adjacent 8 cross 8 blocks I will compose. So, the size would be 16 cross 16. Here also what I will do, because for composition I will use that this transformation matrices as we did. So, it is a composition operation, and then from it I will only take out this 8 cross 8 lower frequency part with the subband approximation scale factor half, and this is my resulting output. Given 4 8 cross 8 block, I am getting 1 8 cross 8 block, and that is how I am also performing image halving. So, if you want to describe mathematically these operations. So as you can see, so this is the composition operations with using these blocks. So this is 0 0, this is index, this is 0 1, this is 1 0, this is 1 1. I mean, I am using x variable to show these are the coefficient blocks. So this is how I am representing them, and then now using this transformation matrix, you get this x 16 into 16. This is the margin block, and these operations are defined in this way. And then you only take out the first 8 cross 8 coefficients. The operations of image doubling also of similar strategy. Here I will first do decomposition of an 8 cross 8 block into 4 adjacent 4 cross 4 blocks, and then I will perform subband approximation. So that is why decomposition followed by approximation. So you see that this is that decomposition operation, and then each one is placed in this 8 cross 8 block where these are all padded with zeros. These are all 0 values, and this part is simply copied with the scale factor 2. That is for subband approximation, the theory of subband approximation what we discussed. And its mathematical description could be in this form, that first you perform the decomposition, you have applied the inverse matrices of this transformation, merging transformation, and then you can use those padding with zeros. So each block is described in this way, and say if it is yij, you can write also in that form. The other technique, that is image doubling, where it is approximation followed by decomposition. So first I will be approximating an 8 cross 8 block coefficients to a coefficients of 16 cross 16 blocks. So which means I have to multiply with the factor 2 this one, and all are set to 0. This is the approximation block from 8 cross 8 block. Its size is 16 cross 16, and then I will perform decomposition. So these operations are shown here. So if once you get the 16 cross 16 block, you perform decompositions to get this one. So these are the results, some example results. So given this is an original image of an watch, this is a watch. So you see that this is image halving algorithm. So it is half of the size in row and column directions. This approximation followed by composition. This is composition followed by approximation. These are the two of different qualities. For image doubling, you are interpolating. So it is, as you can see, it is decomposition followed by approximation. So this is one operation. In fact, its quality is better than the next one. You will see little blurred. First you have approximated, and then you have decomposed it. So two methods, though they provide the solutions of the similar task, but their solutions are not of the same quality. That you can see mathematically also. We can also quantify them by certain measures. Now this is this we have discussed with respect to certain resizing operations of specified factors, particularly of factor 2. That means for half image halving, it is reduced by factor 2, sizes are reduced in both dimension, and for image doubling, sizes are increased by factor 2. But what about that I can resize with integral factors, which means I can convert an n cross n block to ln cross mn block, which means along the direction of columns it would be a factor L, and along the direction of row it will be a factor m. So if so there also first we apply similar approach. So what we can do, first you convert n cross n block into a larger ln cross mn block in approximation, which means the coefficients pertaining to only n cross n coefficients, those are approximated to in this form. once again you see that this is a generalization of the subband theory of approximation. So instead of root 2, instead of 2 or half, here we are using root LM. So in the general case, if L equal to 2 and M equal to 2, you will get back the same theory of image halving and image doubling. Factor 2, it will be of factor 2, as you can see. So once you get the larger Ln cross Mn block, then you perform decomposition. So this is what you do, that you convert a block, n cross n block, into an Ln cross Mn block with this approximation, and then you perform decomposition. So merge L cross M adjacent density blocks, and so this is another approach. So this one is this, but this is the approximation. But this result, as you see, that will not be so good. So I can do approximation and merging, or I can merge, that means approximation and composition, or I can compose. First you can merge L cross M adjacent density blocks, and then you take the first n cross n coefficient, so subband approximation to a n cross n density block. This is for image downsampling. This is for downsampling. So this operation, once again, let me explain you. You are merging L cross M adjacent density blocks. So this Z becomes this one, and then out of them, from there you are taking out these coefficients. So which means you have to divide it by root over 1 by Lm, because you are reducing the size from a larger block. That means from Ln cross Mn block, your output is an n cross n block, which means by a factor L cross M you are reducing it. So we call this algorithm as L cross M downsampling algorithm, or LMDS. Similarly, you can have L cross M upsampling algorithm, where you convert n cross n to Ln cross Mn block, and so this is what you do with the approximation, and then what you do, you decompose it into L cross M n cross n block. So efficiently compute exploiting large blocks of zeros and decompose into L cross M, n cross n blocks. So this is one example for downsampling and upsampling. You can perform also arbitrary resizing. That means, suppose I would like to do P by Q cross R by S, where both are, it can be expressed in the form of rational number. So P, Q, R, S, they are all integers. Then I can perform two strategies. Either I can first upsample, that means what I can do. So this P by Q, R by S can be written in this form, say P cross R by Q cross S. So what I can do, first I will upsample using P cross R factor, that is as you have done, and then you downsample by Q cross S factor. So this is what you do, upsample by P cross R and downsample by Q cross S. Or you can perform downsampling and followed by upsampling resizing algorithm. So first you downsample and then you upsample. So you can see, actually in this case you are doing a lot of computations, because you are upsampling the original, upsampling by P cross R itself. So this will be a computation intensive compared to the second method, but the result also shows that the quality of the result is better for the UDRA algorithm than DURA algorithm. So some examples are shown here. So this is a conversion of HDTV to NTSC format. You see that you have a large image here of size. This format is of HDTV dimension. So this is a standard, that is number of rows is 1080 and number of column is 920. And I would like to convert it to an NTSC format whose number of row is 480 and column is 640. So I applying this algorithm. This is the upsampling followed by downsampling algorithm, and this is downsampling followed by upsampling algorithm. You may notice some more blurring is there in this particular image. Hybrid resizing algorithm, it considers any kind of more general form of subband relation. So it is basically from Q cross S number of blocks, you are getting P cross R number of blocks. So this is the first consideration. See, in the previous case, what happens? A single block is either approximated to make a larger block. So you have an n cross n size and you make it larger to of L cross m times of that block, or you can have n cross n and make it smaller of by the factor L cross m. But in this case, I will consider directly a Q cross S blocks to a P cross R number of blocks and all of size n cross n. So here the approximation of the coefficients. So if you have a Q cross S block and you take P cross R coefficients, so this approximation is a truncated DCT block of X or paired with zeros if required. So this relationship can be captured in various forms. So DCT block of Qn cross Sn and Y is DCT block of Pn cross Rn. So you see that n cross n remains as a multiple because you would like to finally convert them to a set of n cross n blocks. But this resizing operation commensurates with these operations. So what we do, we merge Q cross S input DCT block to form X, then take P cross R blocks to form Y with the subband approximation. So first you merge it and then you take the P cross R block. So this is how this is a subband approximation you do, and there are various cases like P could be less than Q, R could be less than S. So this approximation would be like this. When certain dimension, when it is an upsampling operations in one dimension, then you have to pad 0. If it is downsampling operation, then you do not have to pad 0. So this is how the special cases, 4 such cases are considered, and you have 4 different kinds of approximation arrangements. So this step should consider this computation, but you have to find out in which condition it is, and accordingly this approximation would be there. But finally, what it does, that we are converting Q cross S input DCT blocks to a P cross R blocks, and they are all merged. So you get Pn cross Rn DCT block, and then again you decompose them into P cross R n cross n DCT blocks. So this is how the hybrid resizing algorithm works. So some of the examples could be, so I have just that same image, but I have shown you few dimensions here, like let us see how they look like. So this is a 2 by 3 cross 4 by 5. This is 2 by 3 cross 3 by 2, like this. So this is the 2 by 3 cross 4 by 5 of the original image. So you see that this is 2 by 3 cross 3 by 2. So in the other direction it is increased. This is this factor 3 by 2 cross 5 by 4, and this is 3 by 2 cross 2 by 3. So these are some typical examples of hybrid resizing algorithms. So we discussed about this image resizing operations, and we consider its several different variations, and we can see that directly this computation can be carried out in the block DCT domain using DCT coefficients itself. you can get also as an output as a set of DCT blocks. And then as I mentioned in the complex domain processing, that is your objective, because after that once again you can apply compression straight to that coefficients block. So the next type of operations that I am going to discuss is the filtering operation. So a filtering, let us try to understand, let us have some basic background on filtering of a finite sequence. And once again I will discuss with respect to one-dimensional sequence and then extend these computations for two-dimensional blocks. So if you have an n-point one-dimensional sequence, so you can see that here xn represents the sequence, whereas a filter is given by the impulse response, finite impulse response of that filter, and which is also specified in this way. That means you can consider various things. So these are the points which are specified, but outside that domain what it is there, it's up to you for your computation, but it is sufficient. So normally people would consider that outside this every value is 0, be it input sequence or be it the impulse response of a filter. That is the usual default understanding, but no, it is not necessarily true for every time, and sometimes for the sake of computations we consider certain extended definitions. We discussed these things also during our discussion on image transforms, and we discussed also filtering with that respect. So you will be revisiting them. So padding with zeros at undefined points is a bit natural, and in linear convolution, if I consider this way the sequences are defined, then this operation can be described in this form, so in the linear convolution. So you are multiplying xm into hn minus m. This is what, and then taking the sum. I explained that way this convolution is computed. This is the convolution operations. You are shifting the respective filter response at every instance of input excitation, and then the aggregation of those scaled responses scaled by the input excitation at any time point will give you the final response. So this aggregation is given by this sum. So this is the linear operation it comes, and if I express it in terms of matrix multiplication, so this looks like this. So you can see that this is once again the column vector what we represent here, that is n-point column vector of the sequence, and for each output, and which is spanning from instance from 0 to n plus l minus 1, because till n plus l minus 1 you will have the effect of the input excitation. After that all your input sequence, this after this length nth point, after this capital N, nth point of this sequence, you are padding with 0, so there is no excitation. So the excitation, the response will be felt till the time point of n plus l minus 1. And you can see that this convolution sum of these operations, product and sum operations, are expressed by the respective dot product of the rows and columns in this way. The same thing is expressed. So equivalently, this computation where we are computing at n plus l minus 1 or n plus l time point, I can consider it's a matrix multiplication of this convolution matrix with the column vector, and it will produce me the output column vector. So if I want to get DCT, once again by applying simple linear and distributive property of DCT, what I can do that I can take the DCT of this convolution matrix which is HL. So this is the HL matrix and this is X, this is the x column vector. So density of x multiplied by density of HL should give me density of y. And you know that density of HL can be pre-computed. So in a filter, this is a pre-computed feature. So this becomes a parameter. So for every unknown x, you just simply multiply with this and you get this block. But you can see that this multiplication itself or density of this block itself will not be sparse. Though there are a lot of zeros, but it will not be sparse. So this gain is little in this case. Then filtering with periodic extension of input sequence and response. So as I mentioned that it is not necessarily that it has to be padded, but you can consider another scenario where your input is periodically repeating. So it becomes a periodic sequence. Similarly, your impulse response is also periodically repeating, and incidentally they are of the same period, otherwise there will be a problem. So if it is of the same period, then you can show that your output would be also of the same period, and it is enough to compute with this input and response specification only for n samples of that period, because only one period reconstruction is sufficient. It will be again repeating, so it is not necessarily. So your output would be also of the same length as a result, and this is what is the operation. So this is a periodic extension means that it is repeating after the capital Nth point. So suppose I have input sequence graphically represented like this. Say this is my input sequence for say n equal to 0, 1, 2. My third sample would be also this, then fourth sample would be this, then fifth sample would be this. That means it is repeating. These are repeating. These are going like that. And this is how the periodic extension takes place. In filter response also, it is like this only. So let us see what happens in this case of that convolutions, because I mentioned the result that even the output would be also periodic. So the convolution which expresses this feature through which, so if you perform linear convolution, it will be periodic. So we just simply compute only n samples of that period, consecutive samples, and this could be done using circular convolution, and its expression looks like this. So this is a notation we are using for circular convolution, and you can, once again, this is a linear convolution rule I am specifying, but when I am applying the periodic definition, then I can further simplify it or expand it into this term. So till the small nth interval, it takes like this. After that, as you can see, this value after n equal to n, so at nth point you are computing, this value becomes negative. So next n plus n, if you put, this value would be h minus 1. So what is h minus 1? Basically h minus 1 is, if I put minus 1, it is minus 1 plus n, n minus 1. So your definition, h minus 1 definition is not here, but due to periodic extension, virtually you can get what would be the value of h minus 1, that would be available already in the definition, and this goes till n minus 1 th sample. So this part will be, in this part while computing, you should add n with this time point, so that you get the functional definition of the impulse response with the specified arguments. And this is how the circular convolution is expressed. Now this can be also expressed in terms of matrix multiplication. So this is the column vector, and here we have a column vector of length n. So here it should be capital N, a column vector of length n, you get also a column vector of length n, because you are getting only the response for a single period. And this expression is shown as the dot product of the row vector and column vectors for this matrix. So once again, if I want to perform this computation in the density domain, I can just simply multiply the density of this matrix and density of this matrix, and I will get this one. Now, what happens filtering with anti-periodic extension? Say I consider periodic extension, then another scenario could be extension is anti-periodic, which means that in this case your signal gets inverted with the extended period, and the period of the anti-periodic signal will be twice n. That also we have discussed. So which means, say suppose I consider this is my input signal. So this is say n equal to 0, 1, 2. So that my third sample would be, in this case, would be, so this is my signal now, minus of this. Okay. So the next one would be this. So which means that I have a period. So this is my period and this is my anti-period. This we have explained previously also. So when with this definition I apply convolutions, there also it can be shown theoretically that the resulting output, the result of that computation would be also a sequence. If I apply linear convolution operations infinitely, I am assuming that it's an infinite sequence, then the resulting sequence is also an antiperiodic sequence of the same antiperiod, which means it is also periodic sequence of the same period. The period here is by the by twice n, and antiperiod is length of the antiperiod is n. So let me now express the convolution, and this situation we call it skew circular convolution, and let me denote with this symbol here. So you see that I am applying same linear convolution expression, but since I will be considering the extended values, it becomes negative of what is being specified. So these values are to be subtracted. So these values are to be subtracted from this component, or the negative terms will be negative symbol, negative operations would be appearing here. So this can be expressed again in form of matrix multiplication as before. And one thing I should mention in both the cases of circular and skew circular, that we can make equivalent to linear convolutions by appropriately zero padding. That means in your period would be so large that actually that effect of non-zero excitation would be covered within that length, and whatever zero excitation is there would be nullified, and that periodically gets repeated. So you can always like extension, you made extension on the input sequence, but in input sequence also you can add zeros either in its before and after in such a quantity, so that depending upon the filter length, the number of zeros to be added, so that the effect of the input excitation would be nullified, or would be nullified on the sample. So with this background of convolutions, now let me explain another characteristics of convolution, which we call symmetric convolution. Now in symmetric convolutions, here the filter responses are symmetric over its zeroth instance in the filter response. Since it is symmetric, then half of the response is sufficient. Now, it could be symmetric, it could be antisymmetric also. But only thing is that half of the response is sufficient, specification is sufficient. For example, if this is my filter response and this is the 0th point or point of symmetry, so only these values are sufficient to specify the whole filter. So, once again, if I perform a convolution again with periodic extension of these filter responses, which half of the symmetric, half of the response is only specified, which means I have to first convert it into a full response and then appropriately pad with zeros to to inhibit the excitations of certain length, effect of excitations of certain length. Similarly, again appropriately pad with zeros. Then the effect is that in the type 2 DCT operations, if I take the type 1 DCT of this sequence only, not this sequence, but this half of the sequence, and type 2 DCT of this sequence, then my result would be also of type 2 DCT. This convolution multiplication property I also discussed during image transform, our discussion on image transform, but let us try to understand this part here. So, you can see that I have only considered half of the filter response. So, though in my specification I will take according to my original specification, my input is of length say capital N. Similarly, this could be also of length say capital N, but effectively these operations, so these are of this type 1 DCT and type 2 DCT of same order. So, this is an endpoint DCT, which means that the length, this length should be n plus 1 according to my definition of DCT, type 1 DCT, and this length should be n. Effectively, this is of length 2n plus 1 and this is of length n only. So, this also gives us another flavor, because if I want to perform Gaussian smoothing, I really do not require to specify the whole Gaussian range. So, a Gaussian filter, and that for getting sequences I have to discretize, I have to get the sequences only from the Gaussian filter. So, what I need to specify? I need to specify only this part, and this part is, so this part is not required. Okay. Only this part is sufficient for specification of filter for Gaussian filtering. And this symmetry I mentioned, this is whole symmetry, whole symmetry. So, this multiplication of type 1 DCT and type 2 DCT can give you the respective type 2 DCT result. So, this property if I apply, and then I can get filtering of type 2 DCT blocks. So, I have shown it simply. Now, I have shown with respect to this x2k, this is a type 2 DCT block of say sequence, and this is a type 1 DCT of the filter, and this is how you get type 2 DCT of the response. So, directly you are doing filtering in the type 2 DCT block space, and this can be in the linear transformation form. You can express also as a linear form. So, since it's multiplication of those elements of those type 1 DCT, I can express them as a diagonal element of a diagonal matrix. So, this is equivalent, this operation is equivalent to this one. Now, this is important. So, even filtering is expressed in the form of linear transformation, because what we can do later on, we can see that the series of operations on DCT blocks, say merging or composition, decomposition, approximations, all those things, series of operations can be accommodated under the same linear transformation framework, and you can get composite transformation matrices out of these operations because of this kind of representation. So this is the form we are doing. And in the 2D block DCT also, we apply the same way type 1 DCT block of filter response, then type 2 DCT, and then if I multiply, then it gets a filtered image. We can use separable response. So I have once again discussed with respect to the 1 dimension. In 2 dimension extension, if it is separable, then you can use the respective transpositions, and then you can show effectively for a separable response, effectively this multiplication becomes pre and post multiplications of those diagonal matrices. So this is one result. This is the linear convolution operation, and this is the block symmetric convolutions, and you can see a lot of artifacts in this result. So this algorithm, as I was telling you, it can be expressed in terms of operations, like you should work with larger blocks. So instead of 8 cross 8 block, you can merge larger block, perform the convolution multiplication operations, then again decompose, and you get the filtered image blocks. So these composite operations like merging, then diagonal matrix of convolution multiplication operation, and then again what you are doing, you are basically the inverse is also transposition here. You are again decomposing it. It can be expressed in terms of a single operations. So 3n cross n adjacent density blocks, it shows like this, and this is how you are doing it. So anyway, so today let me stop here, and we will continue this discussion in the next lecture. Thank you very much for your listening.